Hello student, welcome to EPG Pachala. I am Vil Pandian, a professor from All India Institute of Medical Sciences. I am here today to talk about the principles of mass spectroscopy from the paper Techniques in Molecular Physics 1. Let us first understand about the basic fundamental aspects about this mass spectroscopy. Therefore, I objectivize this lecture to understand the evolution of mass spectrometers, understanding the basic fundamentals involved in mass spectroscopy, and the principles involved in the construction of mass spectroscopy. Initially, the mass spectrometers which are used today is not the way how it has been pursued about 100 years back. Therefore, it's very interesting to understand about how this instrument has been evolved over the period of time. Mass spectroscopy is an analytical technique which measures ions by their mass to charge ratio, that is M by Z. As a prerequisite, all compounds must be ionized and made in a gaseous state. Therefore, they can travel in vacuum. As you know well that charged compounds only, charged or ionized compounds only, they can travel through vacuum and they are susceptible for magnetic as well as electrical deflections. In the origin in 19th century, it was developed to identify isotopes. All of you must be knowing about J.J. Thomson when he discovered cathode ray tube and the electrons were passing through the cathode tube. There was a first incident in which they identified that the charged particles can be accelerated in the vacuum and they can be subjected for magnetic and electrical fields. They deflect accordingly. The common unit for molecular weight is Dalton or unified atomic mass unit, that is mu. The exact mass is something that here we use two aspects here, that is, one is exact mass, another one is nominal mass. In your laboratory, you must be seeing a lot of chemicals with the molecular weight or formula weight. This is basically used to roughly represent the total molecular weight of the compound, which includes its acid or basic radicals. It could be sometime it's a sodium salt, that is it's a basic radical, or it could be sulfate, or it could be chloride, that is acid radical. So together it forms a salt, and that salt, when you put it in water, it dissociates into plus and minus ions. Now the problem is that how do you convert these ions which are in a liquid state to the gaseous state, and it should be ionized, it should be charged so that they can be flown through this vacuum. In 19th century, when the J.J. Thomson was developing, he was trying to analyze the isotopes which were, his interest was something different. Those days they were trying to identify new compounds. Therefore, their interest was something they found the same atomic number but different atomic weights. This is something which when we try to adopt the Rutherford atom model, in which they found there is something interesting which is coming up. Therefore, they wanted an analytical instrument which could differentiate and can analyze this. And subsequent experiments in which they were trying to study this, they were trying to apply this principle in different aspects, but it took nearly a century, 100 years, this technique what has been developed by J.J. Thomson to come into commercial use. Let me just show you in 1894, how J.J. Thomson, when he was working with this cathode ray tube, is trying to analyze isotopes. Let me show you one of the ancient, one of the 100 years old machine which was used for this purpose. Interest on discovering newer elements accelerated the developments in mass spectrometry. 100 years before, 1894, J.J. Thomson's experiments figured out the calculation of the ratio of electrical charge to mass of the particles was the initiation of this mass spectrometers. In 1897, early mass spectrometer developed and was used for identification of isotopes. But the final commercial mass spectroscopy came into commercial market about 20 years back. And of course, by that time, almost 6 Nobel discoveries were put together in the construction of this mass spectrometer. What you see here is the rare picture of collutron preparative mass spectrometer which was developed about 100 years back. This picture shows the chronology of the developments happened in mass spectrometer. What you see here is the first mass spectrometer to the left is in 1897 from J.J. Thomson's experiments. And what you see here is in the end towards 2000, you see the development of electrospray ionization, triple quadrupoles, Malditov, and ICP, ESI, all the things developed. The soft ionization technique, that is electrospray ionization, which was developed, that has given a versatility to this mass spectrometer, where we can use a liquid which can be converted into gaseous state, and the molecules can be ionized. The liquid which is present in liquid can be ionized into gaseous state, and that can be ionized. That has opened the era of the commercial mass spectrometers for analytical purposes. The major types of mass spectrometers, if you just look into it, we can broadly classify them into three categories. One is magnetic field deflection, quadrupole mass spectroscopy, and time of flight. Magnetic field deflection, as I told you, that ions or charged particles, when they are subjected in the vacuum for magnetic field, they deflect. So magnetic field has been used for this purpose. So the instruments which are using magnetic field to do this part is coming under the classification of magnetic field deflection mass spectrometers. Whereas quadrupole mass spectrometry is a very significant development, where you applied electric potential to do the job. So as the charged ion path is deflected by positive or negative potentials, these potentials are used in this quadrupole. Basically, the construction of quadrupole I will discuss with you later, and our working principle of it. The quadrupoles are four rods which are rectangularly arranged, also in the square. It's arranged in square, and through which the charged particle is allowed to pass. And the acceleration is done classically by using RF voltage and a radio frequency and a DC voltage, which is alternated to isolate or to resonate a particular mass, so that can be isolated, that can be accelerated, and that can be propelled towards the detector. Time of flight is another one, where a reflectron is used. Basically, again, this path of the ions passing through is increased so that you get a better resolution. The magnetic field deflection and time of flight can give us a little different type of picture as compared to quadrupole mass spectrometry. But as compared to quadrupole mass spectrometry, time of flight gives better resolution in the mass spectrum. This property of time of flight instruments allows us to get high resolution data regarding molecules which are having high molecular weight, which are multiply protonated. Molecules like proteins, peptides, which are multiply protonated, can be accurately measured, quantified by using these instruments. Whereas quadrupole mass spectrometry predominantly is for analytical purpose. Sometimes we use quadrupole coupled with the time of flight together to get the better separation by using the quartz and getting the resolution by using the reflectron. The FTICR is another different another model in which ion cyclotron resonance is used here. Mass tandem-mass spectroscopy is, as I told you, that it can be done by a sequential fragmentation of ions, and it is measured as its fragments. What you see here is the classical U-tube mass spectrometer. In one side, you have a probe in which the sample is getting introduced from the gas chromatography. As you know well, that the carrier gas in the gas chromatography, in which the molecule will be in a gaseous state and it's getting isolated in the column, and it is fed into this mass analyzer where it is meeting the electron beam which is applied on it. Now this electron beam, as I told you before, it gets ionized here, and the ionized molecule takes this U path where it is present in the magnetic sector, or sometimes electric deflections were also used in this kind of mass spectrometers, where based upon their mass, if the ions which are too heavy, they bend too little, and the ions which are very less in molecular weight, they bend very fast, and it could do a small difference in the speed. Thereby, when it is reaching the detector, it's read in the detector. So this is a way that how this YouTube classical mass spectrometer has been used for finding out the mass of the compounds based upon the mass to charge ratio. But this was again, separation of isotopes and for identification of molecules which are in gaseous state, for which this mass spectrometer was used. Here, let me just try to explain you what is this triple quadrupole mass spectrometer. As I told you, that triple quadrupole mass spectrometer is containing 3 quadrupoles. That the quadrupoles, quadrupole 1, quadrupole 2, quadrupole 3. Here the quadrupole 1 is trying to isolate a molecule on its for a particular molecular weight. How it is possible? Let me just try to explain you through this small picture in which you have different colors of flowers, in which particularly you are looking forward for a particular flower. For example, you are looking for hibiscus in this case. So the quadrupole 1 has been aligned to pick up only the hibiscus. So now what happens? Fine. There could be several hibiscus flowers would be having the same molecular weight or same shape in this case. But here, quadrupole 2, what we are trying to do is we try to cut it into pieces. Now the shape, although that 2 flowers of hibiscus look same, they don't weigh same. But when you just try to cut it, the cut piece, now you try to quantify again when you try to again analyze in quadrupole 3, the combination of quadrupole 1 and quadrupole 3 is allowing us to select a particular fragmented ion to reach the detector for its quantification. When it hits the detector, this combination gives us the 3rd degree confirmation for a molecule. First, you are trying to semi-purify the compound before you are injecting into the HPLC or gas chromatography. Once if it is the molecule has been injected, it comes into the ionizer. The ionizer is now ionizing this into its ionic state where it is charged. The charged molecule now, by using this RF radio frequency and DC voltage, it is allowed to resonate at a particular value. Thereby it separates it in quadrupole 1. When it comes to quadrupole 2, it is bombarded with a neutral gas molecule like nitrogen or argon. Here the weaker bonds are broken and it is making unique fragments. Now quadrupole 3 has been set for to pick up a particular fragment. Therefore, the particular fragment is unique identifier of that molecule. The first isolation has happened. The semi-purification is the first isolation. Second isolation happens in the chromatographic column. Third isolation is happening on the quadrupole 1, and quadrupole 3 now it tries to pick up the fragment which is very unique for that particular compound. Therefore, this technique is considered as a gold standard for the analysis of particular molecular for a particular compound. So now here I am trying to explain you how the resolution of the mass spectrometer, how is it very important. Here isotopic abundant, all of we know about isotopes having the the same molecule which is existing in different molecular weights but same atomic number. So here what you see here is hydrogen having 1 proton, 1 neutron, that is deuterium, and tritium is having 1 proton and 2 neutrons. Now the molecular weight is continuously increasing for the isotopes of hydrogen. So we know that for the nominal mass, right, we just take a nominal average weight of this molecular weights. But when it comes to mass spectroscopy, it's very important. We need to know, or we will come to know, about the isotopic distribution. This example on the right hand side upper corner, you see homotroping. It's one of the chemical which is a drug. Now you see the molecular weight which is coming at 276.2 is a major isotope, and what you see here just next to that is 277.2, that is one isotope, one molecular weight above than the first isotope. That explains naturally the isotopes of all elements are existing, and this we know now what type of isotopes are existing for each and every compounds. But when it comes to bromine, for example halides, when you take benzbromine, You see that it's very interesting that what you see here in the lower corner, left lower corner, is bromobenzene. When you see the isotopic distribution, is very interesting. This isotopic distribution says that the second isotope is about 99% of the first isotope. When you just come and see that bromine in the table above, this is what the normal distribution of some common elements, in which bromine 79 is about 50.5% and bromine 81 is 49.5. That is, the third isotope of bromine is existing in a higher amount. Therefore, it is very important to understand with the isotopic distribution of a compound and to understand its property, and this helps in analytical quantification too. This isotopic distribution pattern is a unique identifier to talk about its charge state, and the charge state is very important in determining the molecular weight when it comes for high molecular weight compounds like proteins. As I told you that isotopic pattern is very important for determining the charge state, let me try to explain you how is it important in this slide. In the ESI mass spectroscopy, you get an isotopic pattern. Between the masses, if the change is, the difference is 1, that shows that it is charged, the charge state is 1. But if it is duly charged, is doubly charged, then m plus z by z, the molecular weight what you talk about, when you just apply this formula, you will get it is 0.5. So if it is doubly charged, then the delta m by z is 0.5. So what you get is, for example, you are having a molecular weight of 200. If it is doubly charged, you will get as a molecular mass of 100. Here, the difference between two successive isotopic peaks would be 0.5. This is the simplest example you would be able to understand. When there's the first picture, what you are seeing here is having the difference of 0.5, whereas the second mass spectrogram shows that the difference is 1. That shows the first one is doubly protonated, the second one is singly protonated. So this is the simplest example, but when it comes to proteins, this number could be much bigger than we think of. At the time, resolution of the mass spectrometer is very essential to understand the charge state. Resolution in mass spectrometer, as I told you, it's very important. So how do you calculate this resolution in mass spectrometer? So resolution R is mentioned as calculated by this simple formula, Mn by Mn minus mm. Mn is the highest mass number of two adjacent peaks, and mm is the lower mass number. When you just take a molecular weight 2000, the 2000 divided by 1, that is the difference between the two adjacent peak is 1, the resolution is 2000. But this is a theoretical calculation. When it comes to mass spectrometers, how do we try to do it? When the mass analyzers, when you open the data and you see, you will get a centroid mass. It just takes a peak, and the peak starts and peak ends. The centroid mass, for example, in this picture in the right hand side top corner, the peak starts at 557.13 and the peak ends at 557.7, and the centroid is 557.4. So when you just minus this peak start and end, you will get a value of 0.1923, and by the calculation of full width at half maximum is 557.44 divided by this 0.1923 gives 2898, that is its mass resolution. So this mass resolution of 300 by 0.1 is in this difference will be resolution of 3000. But at the same time, when we get the same resolution at 1000, the resolution is 10,000. Therefore, this resolution capacity of the instrument, which is going to determine how accurately you are determining the molecular weight of proteins. But when it comes to analytical mass spectrometers, unit mass resolution is enough to do the job, because this is involved in the separation technique is involved and fragmentation parameters are included. Therefore, that is enough to do the job. So the resolution is very important for analyzing high molecular weight compounds, the determination of their charge state, and this helps us for the identification of unknown compounds. Now let us come inside the mass spectrometer, the working principle of mass spectrometer. Okay, so now here the mass spectrometer is being kept under a very high vacuum. how much is the vacuum? When you just look at the fluorescent bulb, what you call as tube light, or the electric bulb, fluorescent bulb, in which classically about 1 to 10 torr vacuum is used to reach the complete process of ionization of mercury to give the fluorescence in the fluorescent bulbs. Whereas for mass spectroscopy, the problem is much different. Here, continuously, the sample is fed through an orifice. When it is having an opening on one end and you want to reach the vacuum, 0.7 into 10 to the power minus 5 torr vacuum. That's the very highest vacuum which is essential to make the ions to travel in the vacuum, which you can do all this kind of analysis. To achieve this vacuum, the technology has developed tremendously, which enable us to reach this vacuum. This vacuum is achieved by two techniques, putting two techniques together. One is a static vacuum and the other one is a dynamic vacuum. The static vacuum is achieved by a backing pump which works continuously 24/7. It's like a vacuum pump, reciprocating vacuum pump, which is oil free, which continuously creates some amount of vacuum constantly which is required. Even when the machine is switched off, this vacuum is essential to keep the condition. The second vacuum is the moment when you try to operate it, it allows so much of gases entering into different places. For example, I told you that in the Q2, when you do the collision cell, you need ultra pure nitrogen running at high speed. Now that is also disturbing the vacuum that has to be sucked away very fast. Therefore, continuously that turbomolecular pumps are used to make this possible. This turbo try to develop that much of vacuum constantly. That is a dynamic vacuum which is produced, which sucks when the inflow air which is happening at inflow nitrogen which is happening at different stages, or the vacuum loss due to the entry port where the sample is getting introduced. So a well-maintained vacuum is essential for the function of mass spectrometer, and therefore this vacuum pump, the turbomolecular pump and the mechanical pump together, they try to give enough vacuum. While we compare different mass spectrometers, there are some fundamental aspects which we try to use to differentiate them. One is dynamic range, another one is mass accuracy. The dynamic range is a property of the mass spectrometer over which the linear response is observed for an analyte as a function of analyte concentration. For example, if you just try to quantify a compound of 2 nanograms, when you go for 4 nanograms, 8 nanograms, 100 nanograms and 1000 nanograms. Now linearly is supposed to get the response. Here in the mass spectrometer, the charged ion goes and hits the detector and it gives the response. This response is linear up to some range. This is a linear dynamic range which is unique for a unique instrument. This allows the analyte quantification. If you have a lesser dynamic range, we will be having a cap towards the analytical capability. This determines accuracy, precision of the analytical method. As we know, these analytical methods often go through a rigorous quality control measures according to the guidelines. For example, pharmaceutically, when the drugs are analyzed, they use the criteria called US FDA criteria, ICS GCP criteria. These stringent guidelines are made for each and every aspects of analyte extraction, isolation, and its analysis, dynamic range, and each and every parameter, their reproducibility, their recovery, everything is meticulously calculated. Even if two peaks are co-eluting, two analytes are co-eluting, one should not affect the response of the other one. So these aspects we will deal it when we are coming to do the analysis. At the time I will explain you. But this linear dynamic range of the mass spectrometers, which is going to determine the accuracy and precision. This is limited by physicochemical process, chemical preparation, sample preparation steps, ionization and instrument design, the type of mass analyzer and the ion detection scheme which is involved in mass spectrometers. Next is mass accuracy. Now this is a very important aspect which determines, even we have two class of mass spectrometers, two different class altogether to do this job. And the instrument which is used to analyze the proteins cannot be as accurate when it comes to small molecular weight quantification experiments. One is qualitative, that is, it is trying to get a very high accuracy in terms of molecular weight, because its mass accuracy is 0.0001 atomic mass unit. But whereas for the quantification purpose, we need only unit mass resolutions, where nominal mass 0.5 plus or minus 0.5 is for analytical purposes. This resolution, this mass accuracy, depends upon the resolution how we are trying to take it up. Molecular weight of an ion is likely like sensitivity and dynamic range. Based on the choice of mass analyzer, it could be varying from 0.5 to 0.0001 m by z. This for accurate mass, plus or minus 5 ppm of the theoretical molecular weight is must, so that we understand exactly the molecular weight of the compound. So when it comes to the multiple time protonated compounds like peptides or proteins, you will be getting a molecular weight of 250, but it will be having original molecular weight maybe of 20 kD. Since it is multiply protonated, as the basic fundamental of mass spectroscopy is m plus z by z, that is m plus charge by charge. So when you just add so many charges, if you have 20 charge, the molecular mass plus 20 divided by 20, it will be coming down into a very small molecular weight. But that is not its molecular weight. This determination is done by calculation and considering the isotopic, how much we are getting the resolution in the isotope. Therefore, mass accuracy is a very important parameter in mass spectrometer. Therefore, now as I told you about the mass resolution in mass spectrometers, how we try to, how this qualitatively, quantitatively, we try to use this basic principle of mass spectroscopy to do many experiments. So qualitative experiments, now when we look, qualitative means it's something like you're looking for a good quality data. Good quality data means an accurate molecular weight determination of a peptide is very important to identify that peptide or a protein. But when it comes to quantity, the resolution, even if the resolution is less, and you are able to do the accurate quantification up to femtomole, or you are literally reaching, when you just try to convert into the grams, lesser than a nanogram range to quantify analyte, either it's a biological matrix or it's an environmental matrix, you try to purify and quantify this. So typically different mass spectrometers we employ here, the design, application and the technology almost remains same, but slightly they differ in design to achieve these different purposes. Accordingly, the instrumentation is designed. So the QTOF, the quadrupole coupled time of flight mass spectrometers are MALDI-TOF, but TOF is the time of flight mass spectrometers are MALDI-TOF. These are used to identify unknown proteins or protein determination and protein related experiments for proteomics, protein research, or understanding unknown compounds, etc. When it comes to quantitative experiments, typically we use triple quadrupole tandem mass spectroscopy. Tandem mass spectroscopy means that mass. That is, once one quadrupole is trying to analyze a mass, again the quadrupole 3 is analyzing a mass. Therefore, the name tandem mass. Tandem means one after another. You are having repeats to do the same job. Therefore, triple quadrupole tandem mass spectroscopy, which typically operates the range between 10 Daltons to 2000 Dalton, whereas QTOF instruments work with 50 Dalton to 500 kilodalton. Therefore, these things are differing. And triple quadrupole instruments are typically used in pharmacokinetic studies, drug level analysis, environmental pollutants, forensic analysis, therapeutic drug monitoring, quantitative protein approaches in which there are metabolomics, lipidomics, and quantitative lipidomics. This instrument is used. There is one more type of instrument, that is liquid chromatography coupled ion trap instruments. These are all used for metabolism studies. It is in between these two. Therefore, today we will see about the construction of liquid chromatography tandem mass spectroscopy. For a chromatography analyst, mass spectroscopy is a detector, but a spectroscopy analyst, HPLC, is a sample feeder. So here, the HPLC is used for separating the compounds and mass is used to detect the compound. So together it's a most versatile technique for quantitative and qualitative analysis of samples. Highly sensitive and selective analytical tool when it is coupled with the liquid chromatography for separation of compounds. It selects a particular molecular weight and splices into fragments, which gives a high degree of confirmation, and this also allows us to go with a very small amount of sample which is required for this analysis, and it is considered as a gold standard for quantitative analysis. See, what you're seeing here is LC-MS-MS, triple quadrupole tandem mass spectroscopy from ABSIX, which is in my laboratory, in which we need all these things like nitrogen, zero air, compressed air, dehumidifier, high vacuum pump, and HPLC, and the sample infusion assembly. All these things which are essential to run this machine. So this picture shows clearly is in my laboratory. What you see is a sample inlet, that is HPLC, and an ion source, that electrospray ionization or APPI or APCI, anything can be attached here, which converts this liquid state ions to gaseous state. Then what you see here is a big long metallic tube that is a mass analyzer in which all three quadrupoles are housed, and at the end you are having ion detector, and of course this also does that data collection and interpretation, which is fed into a microprocessor, and it is analyzed according to its mass to charge ratio. What you see here is the inside view of this mass spectrometer about its construction. What you see, this arrow is denoting the place where the ionized molecule is entering into the quadrupoles. What you see here is a quadrupole 1, and there is a box afterwards that encloses quadrupole 2, that is a collision cell where the fragmentation happens. So as the nitrogen gas is, or argon gas is fed into the state, it is kept in a box, enclosed box, where it's a collision cell. And what you see subsequently, again another quadrupole that you call as the MS2. So MS1 is the first quadrupole, then it becomes a collision cell, then MS2 is a mass 2 is the last one. Together they form triple quadrupole tandem mass spectrometer. In a triple quadrupole or tandem mass spectrometer, MS1 and MS2 are mass analyzer that filter ions. The collision cell is filled with argon or nitrogen, and potential is applied to fragment these ions. So this is how that collectively they try to separate, fragment, and reanalyze before the ion reaches the detector. Although it looks very simple, however, its applications are pretty broad. So students, let me just summarize what we have learned so far from this module. We have seen about the evolution of mass spectrometers right from J.J. Thomson towards the commercially used mass spectrometers what we see today, and the fundamentals of mass spectrometers, on what basis we are separating them, how we are classifying them, and parts of mass spectrometers. We just seen about the preliminary angle about it, the parts of mass spectrometers, the type of mass spectrometers, their resolution, dynamic range, and mass accuracy, etc. In further lectures, I will explain you about rest of the things. Thank you very much.